Greetings. This is Lecture 16, OSHA Electrical Safety. I'm borrowing this PowerPoint slide from an OSHA Technical Institute or Training Institute, but I've modified it for this class. The original slide deck was actually about 120 slides. I think I've maybe modified it by at least a third, but I'm going to go through this pretty quick because I just want to give you a quick overview of Subpart S under 1910. Give you some other information, and then there's going to be a second video. Then that's the one that's been kind of holding me up, and I'm going to kind of want to show you the components or electrical system design for a residential home, using my home as an example. I also want to share some of the results of my consulting. So for lecture 16, what I'm going to do is have this lecture. I'm going to have the old one you can refer to, and they are the ones that, what I do is I cover those lectures there. And so I'm going to kind of indent those after I complete this one and post this one. Please watch the basic electrical safety concepts. It's 4.5 minutes. And then check out these other links. So this is some really, really great information. It may look like too much, but what I want you to do is just kind of take a look at it and see what you think. In lecture 17, I think is that's where I'll move my new video I'm going to create and then talk about arc flash. This is from a link. The stats that were on this before were kind of a little bit. So electrocution is not a common occurrence in the workplace, but it does happen. Here it's saying just all over the place, approximately 100 deaths per year. I think about half of those are work-related. And it says approximately 400 due to high voltage. Lightning causes anywhere from 50 to 300. There are about 30,000 plus shocks. I've been shocked before. Let's see. About 20% of all electrical injuries occur to children, just accidental. They probably are just messing with a power cord. It's saying that it's the fourth leading cause of work-related death. Comes and goes, depending. So here's all the different types of outcomes that are a result of being exposed to electricity. Electrocution is death through shock. Electric shock is when you just you become part of the circuit, but it doesn't necessarily kill you, although it can still harm you and kill you later. And we'll talk about that. Burns, and that's primarily what you get out of it when it's electric shock. Well, I'm not going to show the pictures. I think I did in the other video. Falls are pretty common too. Two reasons. One is you might be working at a height, especially if you're doing something in the ceiling or on a roof or overhead lines. And then if you do get shocked, it tends to send you flailing. But also you may just be shocked and then you lose your balance or you jump back. That's what tends to happen. There are some terms that you need to be familiar with. Current, resistance, voltage. That's the main three. Conductors, and you're probably reading these just as fast as I can read off. So a conductor, it says metal, but a lot of things have some level of conductivity unless it's an insulator. An insulator doesn't let electricity flow through it. Because, electricity is just free-flowing electrons, really. And then grounding is basically a conductive connection to the earth, because that's where electricity will dissipate. So when it says ground, they mean ground. The term you need to know is Ohm's law. Ohm's law is how they calculate based on a voltage or a resistance or a current or the power supply what you can expect. I'm not going to get really into the whole physics of electricity, but here I got one example. So I've got the Ohm's wheel on the left. On the right, I've got an example. So here's a circuit. And it's saying that we've got a resistor in here. We've got a current of 5 amps. What is the voltage? And the voltage would be 1,000 volts, which is quite a bit. That's a lot. 5 amps, not too much. So it must be the resistance. So a shock is when electric current flows through the body. So the body becomes part of the circuit, typically being the ground. Usually it travels through the body to the ground unless you've made contact with both the what we call the hot or the energized pole. And when I say pole, I just mean energized part, wire, whatever it might be, or the neutral, because all of our power is alternating current, so it's going back and forth. If it's direct current, then that's traveling from one place to another. So if you If you make contact with both poles, then you're sending it back through the circuit itself. Otherwise, it's flowing through you to the ground if you have a connection or contact with the ground. A lot of people think that electricity flows through the path of least resistance, but a friend of mine said that that's incorrect. A majority of it flows through the path of least resistance, but it goes through all paths. So you may get a lesser shock if you're not the path of least resistance. And it says, you've probably already read here, different severity depends on all these different things. The time of year, gender, all these things dictate how much resistance there is in your body and how much electricity can flow through it. And it says low voltage is not a low hazard. That's true. It just depends on where it enters the body, where it leaves the body. Currents as low as 75 milliamps. And down the bottom, I showed you what that is. That's 0.075 amps. That's very low. That's a very low number. Can cause a ventricle defibrillation if it goes through the chest cavity. I mean, if you have an electric current that goes from like your pinky to your thumb, it's not going to do anything to your chest. It has to flow through your chest to cause that. But I think we've got a good chart. Electric harm. So common household breakers are 15, 20, and 30 amp. Cardiac standstill, 2 amps, 100 milliamps. Ventricle fibrillation threshold. So before it said it was 75. Here it's saying 100. So there may have been a protection factor in the last number. Paralysis of respiratory muscles is 20 to 30 milliamps. 16 milliamps current charge average person can grasp and let go. So that means you still have muscle control below 16. 1 milliamp, you can barely perceive it. Yeah. So as I had said, this is how it happens, and this is kind of meant to be cartoonish. And it's most dangerous when it flows from hand to hand. So it goes through the center of the body, or hand down to the opposite leg. So again, the path depends on how dangerous it is. And this is how it harms you. The current flows through flesh. It heats up the flesh. Given a high enough voltage in the right condition, it can actually flash boil blood and cause a small explosion. Now, when we do sense it, we tend to get thrown. So it's usually a very quick path, and then the circuit is broken. But if a person is holding on to something and it causes them so they can't let go, it will cook them. And there's a video on YouTube. I'm not going to show it to you because it is pretty bad. It's got 4 guys pushing a mobile scaffold, and they weren't looking up above, and they contacted a live overhead line, and they just basically all fell, but they didn't let go. And a couple of them catch fire. A couple of them just start smoking until it burns off the arm. So just describing, you're probably like, ugh. Some of you might be like, well, cool, I got to go find this. And you can find it online. I'm not going to make you watch it. Kind of like if you said Jaws 2. Now, I don't think it was the best of all the Jaws movies. When the shark bit into that power line. It's kind of like that. Not like it, but kind of. Another thing is inadequate wiring hazards. You have to choose the right gauge wire, and you see they've got the wire gauge here. The lower the gauge, the bigger the wire. I know that sounds weird, but the 0, or what they say knot, is the biggest. But they have double knot and triple knot size wires. Those are big wires. And in the other video that I create, I'm going to show you some. I've got some stuff here, but I'm not going to bring it in because I need to speed this up. But if you're trying to force too much power or too much amperage through a certain diameter of wire, all those electrons cramming together release heat. And that heat can damage insulation or electrical components. And then when electrical components become exposed, they can arc, they can spark, they can cause fires, they can cause arc flashes. So you want to make sure that the allowable, so you're designing the system for what you need for power, and then you have an actual design component, either a fuse or a circuit breaker that will handle, it'll monitor it. So if too much current is being pulled into the circuit, it trips it and doesn't let any more power go through. So make sure you design it properly. So we're going to quickly go through Subpart S of 1910. I'm not going to go through the 1926, but if you want to go look at it, I was going to copy and paste it on here. It's long because they have a lot of reserved sections. So there tends to be like 3 different parts of Subpart S that we're going to focus on. NFPA 70E is what we're going to talk about in Lecture 17. It has to do with arc flash. So here, we've got 302 through 308 and 399, and I think there's also some training standards in the middle, and that might be the 31 to 60. Oh, maybe that's practices, yeah. But we're going to spend most of the time on the lower numbers, the 302, 308. So 303. All conduction equipment must be approved, so there should be a sticker on it. Somebody should have tested the system, and there should be a sticker verifying what it is. United Underwriter Laboratories. There are all kinds of different approved labs that test these things to make sure that it is a properly designed electrical system. Here's an ETL. That must be another lab that tests things. So you should, on any piece of equipment that can be plugged in, you should be able to see some sort of stamp or label indicating it's been tested. And also there should be specifications on how it can be used. For instance, a multi-strip, and I should have had one here to show you. You know what they are. Everybody uses them. Those are only designed for very low voltage, so you should only be plugging in TVs, computers, Xbox, things like that. Something that draws more current, like a refrigerator, a compressor, a hair dryer. These types of things draw more current. You should never plug those into a multi-strip. They're not designed to be able to handle it. And you may actually be using a multi-strip that's designed for a 15 amp max, but then you plug it into a 20 amp or a 30 amp circuit. So you would melt it before it would trip anything. Let's see. Yeah, make sure things are protected. Make sure things don't deteriorate. If any part of an electrical circuit or electrical system design or the equipment is damaged, it should be taken out of service. And unless you have somebody who's qualified to repair it and test it and put it back in to service, it should be replaced. I've cited that before with OSHA. You shouldn't have dissimilar metals contacting each other. We typically have copper lines, but in the olden days they had copper and aluminum, and you'd have special connectors, special systems for it. It's better if everything is just copper. Make sure that you use something within the manufacturer or the ratings. I once cited a place because they were using I might have one right here. Yeah, I do. You guys know what these are? You can set this up and then plug in. You see, it doesn't have a ground, so it's very low voltage. Plug in like a lamp or something, and then you go on vacation, and then it turns on, and shuts off at a certain time. Well, apparently they had like a commercial-sized coffee maker. I mean, it was a big, huge thing in their break room. They provided coffee to their workers, but I guess they had trouble with people not turning it off at the end of the shift, and it had damaged some of the pots. So they plugged it into one of these. I looked at it's got a UL rating. It tells you what can be plugged into it, and it's got all of its, what it should be used for. But when I looked on the back of the commercial coffee maker, it was not designed. It would have overdrawn the device. So luckily I caught that, and it just happened to be luck that I looked behind it. Though I always look for electrical things, because especially in kitchen areas, I'm checking for ground fault circuit interrupters, which will come up later. What this is showing is just a basic design for. Over on the right, you've got 4 different pieces of equipment. They call them motors here. Each one should have an individual shutoff. Because if the shutoff is at the circuit level, you'd have to shut it off, and then all of them would have to be off at once. And usually you just want one down or one turned off so you can work on the other 3 are still working. It's a better designed system. Though I don't like the bus conduit there at the bottom. Those are very dangerous because those can energize. Rarely at home would you ever have to deal with anything 600 volts. That's industrial. That's overhead power. But those need to be it says right here, it should be labeled for 1. This is talking about 600 or lower. Okay, so guarded, illuminated, things like that. Anything above 50 volts has to be guarded. 50 volts is kind of low. If you've got things, if you can't fully guard something, it can be held behind an access controlled enclosure. Make sure everything must have access. If you can't get at it, then people won't maintain it. People won't use it to lock things down. So you always have to have clear access. Just like you need clear access to fire extinguishers or clear access to exits. Your electrical system, or the switches at least, need to always be accessible. And that's something I've cited before too. Polarity there's, and here they have a picture of an outlet. Here I've got just a real basic 15 amp outlet. Now how do I know it's 15 amp? Because it's just got the straight lines here. If you ever look at an outlet and it's got a horizontal line, I think it'd be right here, that's 20 amp. So that's how it's labeled. It's got almost like a brass type color and more of a polished silver type color. So what we have here is the silver is always neutral and the brass colored is always the hot line. Yeah. And this looks like it has 2 different types of connectors to it. It's got a compression fitting behind, or you can wrap the wire around it. I like to wrap the wire so I'm assured it's on there. Then I tighten it, and then what I do is I wrap electrical tape around it to cover up the poles so there isn't some sort of incidental contact if you were to be pulling this out and you haven't de-energized it. Reverse polarity would be it's hooked up on the wrong side. Your equipment will still work, but there are some situations that would cause you to, it'd be dangerous. And so it's just better to obey the design of this. And then also we've got the little green screw, and that's ground. So you're supposed to hook up the lines properly. And you can test whether that is there or not. Receptacles and cord connectors, ground type for 15 amp and 20 amp circuits, which is typical for home. Grounding contacts need to be grounded. And you can test that. I've got a tester and I'll show that in the next video. So you got the ground, I believe, yeah, so the smaller hole is the hot and the bigger hole is the neutral. You need to know that. Oh. Sometimes you need ground fault circuit interrupters. That is a component that detects a differential in the current flow. I believe it's really low, like 5 milliamp difference. So it's alternating current, but if it's finding that it's being released, so it's being delivered and not being used, which would be going through a person or through a ground, so it's a ground fault circuit. So then it breaks the circuit. And I think it's like less than a second, so it's meant to save lives. You need them in bathrooms, you need them in garages, you need them wherever there could be a wet surface, in which it enhances the chance that a person would be the ground, or it makes the trip to the ground easier, so therefore you put the ground fault circuit interrupter there. You have to make sure that there is disconnecting means. So like in a home, that's the circuit breaker. In businesses, there could be a sub panel or something that has just a switch. Yeah, it just depends. But anything above 600 volts needs to be properly labeled, contained, protected, because that'll definitely kill you. The other stuff could. 600 volts will kill you. For 600 volts or less, protecting conductors and equipment, overcurrent devices readily accessible, shielding to avoid burns, on-off position clearly indicated, vertical up. So do I have a switch here? Yeah, so you're supposed to put them in. This is actually a 3-way switch, so it's not labeled off and on. So up is on, down is off. That's how you're supposed to design it. But when it's a 3-way switch, it's going to, depending, because that means you have 2 in a room operating it. You're not going to have that. And so it also, I think in here, it has to be of proper functionality so that if you turn something on, gravity doesn't turn it off, which that would be a very overused circuit. You should be able to always test the ground, make sure it's functioning properly. It says protects circuit from lightning and other high voltage. I'm not sure if I fully agree with that. You can still damage equipment even though you have a functional ground. Because again, electricity flows through all paths, not just the path of least resistance. It does stabilize the system though, provides protection. GFCI is not an overcurrent device, such as a fuse or a circuit breaker. GFCI is for when there is a slight differential, whereas the overcurrent device is designed that if you're trying to draw too much through that device, it shuts off and kills the circuit, stops delivering power to it. All right, so we're in 305, and I'm going too long, I apologize. Temporary wiring, extension cords, typically. Not favored because it's exposed. It's an exposed wire. It doesn't take much to pinch, a line, and then you have exposed copper. And so what they want is they want you to put in permanent wiring, because a permanent wiring system, permanent electrical system, is designed to only function as it's designed to do, whereas an extension cord can be misused and it can be damaged. And you'd rather have the lines behind the wall or secured in a conduit than you would out in the open. Here shows some people, you're not supposed to run cords through doorways or around metal edges of shelving. And I see that a lot. I've seen that a lot. And sometimes people think that, I'm just going to use this extension cord for all of time. Anything beyond 3 months, you should just put in a new circuit, which I do in my house all the time. It's very easy and it's not that expensive. I actually enjoy that's why I'm going to try to make another video showing you things I've done. I enjoy it. I think it's fun, which is sad. Cabinets, boxes, and fittings. It depends what you have in the wall. I've got a bunch of stuff here. So this is a remodeling dual box, because I can cut a hole in the wall and then I can screw this in, and this snugs up against the back of the drywall. And then I run my lines through these they're a knockout, but they pinch it, so they provide some protection. Versus, I've got some other stuff I'll show you later. I don't want to go too much into it. Flexible cords. Yeah, I talked about this stuff. 306 gets into specific equipment, electrical signage, cranes and hoists, electric welders, so arc welding. We have welding coming up in a different, but it can be dangerous too. Hazardous locations. We'll talk about this kind of stuff, especially when we get into confined spaces. But if you're going to be in an environment in which an arc could ignite either combustible materials, flammable liquid vapors, or what have you, combustible dust, then you really have to be careful. You might have to have something called intrinsically safe electrical, which means it's completely contained away from the environment. Oh, intrinsically safe. It refers to NFPA 70. We'll get into 70E in the next lecture. Or special systems. I'm not talking about too much about utilities. That's something much grander. It does address solar photovoltaic systems, basically solar, and that's what I have in my home. And so if I am able to create this other video, I'll show you the system I have at home too. I don't have a charging setup. Those are expensive, and I've just a direct delivery, and then any overflow gets sold back. So I've got a special meter on my house that measures directionality of power, and I think it does it like every 3 seconds. I was out there watching it earlier today until my phone failed me. That's why this is taking so long. Safety-related work practices. There's qualified people, unqualified people. Qualified are the ones who are trained to be around electrical hazards. Even though you do want to de-energize, unqualified persons should not have access to it. And that's everything above 50 volts. They can't go near it. Yeah. Although I think there was a ruling, 50-60. So I think 50 is what OSHA goes by now. Yeah. Selection of work practices. So everything should be de-energized. Again, there's the 50 volt thing I talked about before. We'll talk about lockout tagout next week. Yeah, we'll talk about that next week. I want to cover this first. Yeah, lockout takeout basically, and this is just for electrical, and there are other forms of energy that need to be isolated or de-energized and controlled, is that if somebody's going to work on a piece of equipment, you want to make sure that piece of equipment isn't running. Not only do you not want them exposed to electrical hazards, but you don't want the machine to start up because that can cause problems too. And there's a systematic way to go through and turn off a circuit, lock it and put a tag on it so that you're the only person who's able to turn that back on again. Because you put a lock on there, you have the only key. The tag indicates to anybody else who has it. Okay, we'll get into that later, of course. Yes. For overhead lines, that's a whole nother issue. It's high voltage. You should never come within 10 feet of an overhead line. And as it goes above 600, I think it's another few inches every 50 or 100 volts or something like that. Oh, there we go. 10 feet plus 4 inches for every 10 kilovolts. You should never go near it. If you're ever at a home and you've got an entry point that is, comes from an overhead line into the house, mine is underground. If you ever have to go do work on the house, such as siding or your gutters or whatever it might be, contact your local utility and ask them to put protection on that line, just so you don't accidentally contact it. I mean, you may not contact it, but maybe the ladder slips or you drop a tool or something. Never ever go near it. Stay 10 feet away. I mean, it's also a hazard for people who are driving extended arm fork trucks or other sorts of devices that go up and down, because if you are moving and you contact something with a metal chassis, you can energize that chassis and then you're just getting cooked. Portable electric equipment, you basically should be inspected, make sure it's in operating condition, and it's only used in the ways in which it was manufactured. So you do a visual inspection, check the plugs, look for damage, take it out of service if it's not up to par, basically. Don't use it in wet environments or conductive environments. Make sure ground is maintained. Never plug or unplug live equipment with wet hands. Protect hands. Use locking connectors. So that's an interesting point. I don't have an example readily here, but if you've ever plug something into the wall, and let's say that the outlet's old, and so it doesn't grab it, and it starts pulling away, and you can see the metal, that's exposed. That's a live metal part that's exposed. You could touch that. I actually was shocked by that. First time I was ever shocked. I was trying to pull a cord out of a multi-strip, sticking, and to get better grip, I put my fingers around the plug to pull out, and that's how I got shocked. It was right here. And it kind of goes numb. Talks about using testing equipment. I've got testing equipment. I'll show you that later. Safeguards so we'll talk about PPE when we talk about arc flash. There are other standards. So there's the construction. There's another consensus standard out there. You can see that's the API RP. Clues that electrical hazards exist. Trip circuits, blown fuses, warm tools, wires, and that I've done that before too. GFCI that shuts off a circuit, Warner freight insulation. These are all problems. Somebody got creative and they used what looks to be a dish soap bottle, turned it into a box. Can't do that. It's not designed for it. Here, someone tried to get cute and they used a junction box to service two different multi-outlets. You can't do that. Somebody used a drill bit as a fuse. Can't do that. Well, it looks like a line was fried. You can see that there was an arc here, arc event. Melted part of the sign, and you can see how it's all fried. What happened? I wonder if the sign, maybe the sign, because of wind, pierced the cord, and that's probably what it was. I bet that's what it was. So you can't be hanging metal signs near a conduit like this. It pierced it. That must have been it. The wind must have moved it. Here you've got a damaged strain relief on a cord. That has to be taken out of service. I think that's pretty self-explanatory. Needs a cover. Obviously, rodents can actually cause problems too. There are other resources as well that you can have, but I gave you probably the best ones I could find. I'm sorry that took so long, but I covered the basics of what OSHA says and combined some of my own stuff. In the next lecture, we'll talk about arc flash. Please watch the electrical basics video from YouTube, and check out the one I had posted before. It kind of covers more of the things that one of my guest speakers used to cover. And I'll try to get a residential electrical safety video posted in the next lecture. Thank you.